My name is Vyacheslav. Friends call me Slava. All people are my friends, unless they write JavaScript. No. Anyway, so I'm here to talk about JavaScript performance, and this talk is a little bit different. I looked at the schedule, and all talks are mostly about using JavaScript, and so they are targeted to JavaScript programmers. But my talk is a little bit from the other side, from inside the trenches. It conveys my perspective on JavaScript performance based on my experience working on the V8. I worked on all kinds of different virtual machines in my life, starting from Java, VM, and I also worked on things like V8, which is a JavaScript engine inside Chrome, and Dart VM, and the Luajit even. But this talk is concentrating on my experience on V8. So. And why is it important to know how V8 works? Well, that's because all VMs are very complex, and to understand the performance, you really need to understand how VMs work. So, for example, this is a Stack Overflow question from today. I edited right in the morning. So somebody is very curious why on the Node.js. So how many people use Node.js? Okay, a lot of you. My condolences. Why on Node.js let-based for loop is slower than the var-based for loop by a considerable amount, maybe 4 times. It's an empty loop, so why empty loop is slower? So the overhead of loop in itself is considerably higher. And usually you have no choice but to ask a question on Stack Overflow if you encounter the problem like that. But in reality, if you are prepared at least a little bit, then you can have a choice. You can go try to profile what virtual machine does, or you can at least try to read the code that it produces, or maybe the code of the virtual machine itself, if you can cope with C++ and don't need a bucket for that. And not many people can cope. For example, the V8 has this optimizing compiler called Crankshaft. And if you want to deal with Crankshaft, you can use a small tool that I wrote that allows you to read the code that it generates. Using this tool, you can look at what happened with that for loop. And it probably is a little bit hard to see, but this is the code of the benchmark in the form of the control flow graph that is used by the optimizing compiler. And it doesn't really matter what actually happens, but you can see some suspicious things are happening because you have the loop with for var up there, and somehow there is a very big loop down there, which is considerably bigger. And what's most suspicious is that there is a loop inside the loop if you use the let binding in the for loop. This is really strange. And actually, the let bindings were added after I already departed from V8, so I was curious myself what's actually happening. And the way I was trying to resolve this, I didn't know actually what is happening. So I got the source of the V8. There are instructions how to get it. And I built a debug version of V8, which is very easy to do on Mac, for example, or Linux. A little bit hard on Windows, but development on Windows is hard anyway. You cry all the time. And then I ran this version, passed the test file to it, and I asked it to print the abstract syntax tree that it builds for this code. And it looks very kind of scary. It doesn't matter what actually happening. I will say it doesn't matter what actually happening a lot in this talk, because you really need to concentrate on some points in the code and not pay complete attention to what is happening. And if you just start reading through it, then immediately what jumps is that there is your normal loop variable, I, and then there is this strange temporary. And unfortunately, it doesn't fit into the screen, but it says .for. So obviously, your original code did not contain any variable called .for. You can't even create a variable called .for in JavaScript. So this is immediately really strange. So you go and, oh yeah, here is a smaller version. So you go and you just grab the sources of V8 for this .for thing, and you find it somewhere in a strange header file called ast value factory. And there is this thing called _4, and you say, okay, maybe I should grep for that now. And you grep for that, and you find the code in the parser, and it doesn't really matter what the code is. It's just enough to know that it's in the parser. Then you go start reading the code around these places where it mentions .4, the ._4, and you immediately find a helpful comment. So the V8 sources are relatively well commented. So you can find this comment there which says, okay, we have this for loop with the let or const binding, and we rewrite it as follows. And what follows is a huge rewriting rule for this. And it's all in the comment, and immediately you can see where the loop inside the loop comes from. There is a loop inside the loop here. There is this loop, and then there is this loop. And I can't really give you insight into V8 implementers' brain, why they decided to implement it this way. But I guess that was because they wanted to shoehorn the let bindings into the like old AST. And as a result, they got somewhat inefficient implementation of that for the for loops. So hopefully they will fix it. And things like JavaScript core or like Firefox, as far as I know, don't have this, the spider monkey, they don't have these issues. So eventually V8 people will probably fix it. So there are 2 points of view here, is that internals are important and you really need to know them, but there is also a point of view that internals are completely irrelevant and you don't really need to know them. And both of these are valid. So I don't want to try to persuade you that you need to know everything that happens within those many lines of C++ code. But you need to have the understanding on a very high level, because when it actually matters, it matters a lot. So for example, here's a chunk of code from some Russian like social site where people talk about programming. Somebody tried to measure something, and they wrote this code. And everybody here can read JavaScript code, so I'm not gonna go through that and explain what it does. And they run it. They called this find function many times, and they discovered that you can do it on V8 on Node like 5,000 times per millisecond. And that sounds pretty cool. And then they tried to do this. They said, okay, what about if we cache this array outside of the find function? Oh, actually outside of the index and outside of the find function. And how much does it improve performance? And it does improve performance. Now you can call it 14,000 times per millisecond, which kind of makes sense. You don't allocate array every time you call the index or find. And then they wrote in this post, they wrote that, oh, that means array allocation is expensive. And I came into the comments. I like coming into the comments and telling people that they're wrong. And I said, what about if I make a function that makes an array? And instead of moving the array allocation out, I kind of move the function that creates this array out, and I will start calling this function in. So logically speaking, it should again drop the performance down, all the way down to like 4,000 or 5,000 operations per millisecond, right? But actually it does not. It actually is almost as fast. And this is what people do when they see this. They are very surprised. And here the choice is to profile. Like you can use on Linux, for example, there is a very helpful tool called perf, which is a thing that can hook into the CPU performance counters and aggregate the statistics for you. And V8 has certain levels of integration with this tool. So with the newest kernels, you can even get the annotations like per assembly line, essentially, per machine code instruction. But with an older kernel, you at least get the per function statistics. And what does performance counters show here? That there are a lot, the names of functions in C++, they're very long, right? They don't fit on the slide. But you can see that there is a lot of stuff related to creating new functions here. It's a lot of C++ code responsible for that, because it says new function, new function, new function, new closure, so on and so forth. And if you profile the version where the array is allocated in this small helper function, you discover that there is no such thing happening there. But there is instead a thing called fast new closure stub. And what happens here is very kind of bizarre. Is in V8 there is this thing handwritten in assembly, essentially, that can allocate closures fast, but it does not support, or it did not support allocation of closures, a fast allocation of closures, if the closure contained an array literal inside. So what actually happened? Let's go to the code, back to the code. When you had an array inside of the index function, the allocation of an index function itself, which happens every time that you call find function, was very expensive. It had to go to the runtime and do all the stuff in the runtime. And as soon as I moved the array allocation out, then the allocation of the index function was sped up considerably. And even though that you allocate both a function and the array, every time that you call this, the allocation itself is not that expensive because it happens in the new space. It's just a bump of the pointer. It's very, very fast. Okay. So if you run this code on the newer V8, then the V8 people actually taught this handwritten piece of assembly how to allocate closures with literals inside. So now both cases are equally fast. Okay, here's another very interesting example from Stack Overflow. Somebody wrote a CHA-20 cipher in JavaScript, and it does not matter what CHA-20 is. It's just some number crunching stuff. Yeah, that's essentially it. It's the main part of the CHA-20. And there is a helper method called QuarterRound here, which is called a lot of times in the loop. And the person who asked the Stack Overflow question, he was actually curious. What happens if he takes the implementation of this QuarterRound and inlines it into this function that calls it? So he measured the version without inlining, and it was like 20 megabytes per second. I don't know whether it's fast or whether it's slow for a cipher. It doesn't matter for the purposes of this talk. Then he takes this implementation of this function, QuarterRound, and just puts the code into this loop manually. Completely inlining and turning this loop into a huge mess of the arithmetic. And he runs it, and of course the expectation is that it runs faster, but it actually runs 10 times slower. So he makes the face like that, I guess, and is not very happy. And he says, I heard somewhere that inlining must improve performance. Why does it not happen? And I looked at this example and I said, well, you have this function there, which does certain things to the numbers. And what if you apply the ASM.js to it? And ASM.js is this interesting standard where you put the use ASM annotation into your code, and then suddenly everything runs very fast. So I said, put the annotation use ASM in your code like that, and the VM will speed it up. And lo and behold, it did speed everything up, back to basically the same performance that was there before. And of course, you need to put an additional comment there which says that to the people who don't understand anything about performance or virtual machines, otherwise they will remove this. So, and that's why you really need to know things. Usually, when we say performance, we used to mean that you go to jsperf.com and you write some micro benchmark, and you know everything there is to know about the JavaScript performance. But JSperf kind of died. It's now in this perpetual state of rewrite, and you can no longer use it. So JSperf, for those of you who don't know it, like how many people ever used JSperf in their lives here? Not that many. Oh, that's good actually. You are not spoiled. Your minds are not corrupted by this thing. So it was this site where you could write some code, and then you press the button run tests, and you get like operations per millisecond for those tests that you wrote. And other people could also run those tests, and then the data was aggregated, and you could see in different browsers, different OSs, some average performance numbers. But the problem is that people write very strange benchmarks, and they don't understand how to use it correctly. So if you base your decisions on this, you get really strange decisions. For example, somebody tried to write this test which tries to measure what's the fastest way to count letters E in the text. And they discovered some very fast ways. On Firefox, you can see, so this is operations per millisecond or per second. So the higher, the better. And Firefox, there is this purple line that like is huge. Like it's faster than anything that you saw before in your life. It's like Tesla of JavaScript. And it's this split thing up there. So the fastest way in Firefox apparently to count letters E in the text is to split it by letter E and then take the length of the array and subtract 1. It returns the right result, kind of, but it's kind of, what? What actually happened here? And the other one that is also fast in all the browsers, not as fast as the first one, of course, but still very fast, is to iterate over this string. But for iteration, you don't use the normal, like for I from 0 to length of the string. You start slicing the string with a slice. And this is kind of, again, strange, because what? I would expect slice to be slow. So it's really strange results. And if you take it like for the face value, you will make strange decisions based on that. And you shouldn't do that. So you should instead doubt everything, like literally everything. You should doubt, if you're going home, you should doubt whether you took the right bus. And of course, you should doubt the micro benchmarks. So the micro benchmarks is this like thing that you try to use when you want to measure what's the cost of a single operation. And how do you do that? Well, of course, you write the code like this. You take the current date, then you perform the operation, then you subtract the current date. You subtract the previous current date from the current date, right? And you get kind of the length. Okay, simple enough. But what if the operation is faster than the clock? Usually, you would expect that the assignment to a variable, for example, does not take a millisecond even, right? Well, maybe it used to take a millisecond back in the 90s, but not now. So the easy answer is just to repeat the operation multiple times and then divide the time by the amount of iterations that you took, or divide the amount of iteration by the time. Depends on what you want to get as a result. So this is the arithmetic from the school, but maybe not everybody went to a school, so I will repeat a little bit. So you want to find the cost of the operation marked C. So if you repeat it n times and then you divide it by n, then n goes away and you kind of get the cost, right? Arithmetic 101. So if we look at the example with a slicing of a string one by one, then what happens with this example, what makes it so fast, is that the JS-perf, or the benchmark.js, which is this library underneath the JS-perf, it generates a JavaScript code wrapping this into the loop. And maybe if we spend an hour just staring into this JavaScript code, we will figure out what the bug is. The bug is that you arrive with an empty string on the second iteration of the outer loop, right? You slice the string, slice. It ends when the string is empty, and then string is never reinitialized. You just repeat with an empty string all your operations. So repetitions start with a string equals to the empty string. And we wanted to get math like that. But we actually got the math like that. So we repeated an operation once, and then we repeated nothing n minus 1 times. And then we divided by n, and you got the cost of operation divided by n, and the cost of operation is a very small number, and the amount of repetitions is very high. So it's approximately, it costs nothing, right? So very simple math. This is a very common example of benchmark.js or JS-perf misuse, when people don't take into account that operations should take the same amount of time every time you run it. But it's actually not very easy to achieve that in the modern world. So for example, here another case from the JS-perf where somebody tried to measure what's the fastest way to convert a string to a number. And it turns out, again, on the Firefox, the fastest way to turn a string to a number is a double tilde. So if you know the intricacies of the JavaScript semantics, the tilde is a bitwise negation, right? And the double bitwise negation is not a negation at all, right? It's just identity. So, and then you declare, okay, double tilde for the win, let's convert all parse int to the double tilde. They're considerably faster. Of course, the answer is nope. JavaScript compilers, the just-in-time compilers, they're relatively clever like dogs. They're not smart as people, but at least they can do woof woof to your code. And they can observe how the program is running, and they can optimize while it is running. So your math from the first grade no longer applies really. You get at least unoptimized version and non-optimized, unoptimized version and optimized versions together, and then you repeat several times the unoptimized version, then JIT comes and optimizes it. So it gets a little bit complicated. But it actually is even more complicated because there can be multiple optimized versions. Like Safari, for example, it has several optimizing JITs, and it tiers up as your code runs and becomes hotter and hotter. And if you factor in all kinds of costs like GC and compilation costs, then the math really becomes messy, and you can no longer use a simple math. You need to go to the university and take some analysis. So you need to outsmart the just-in-time compiler to measure anything, really. And if you program languages like Java, for example, then you already have tools to do that. For example, the Java has the Java Macro Benchmarking Harness, GMH. And it had a lot of engineering put into it to outsmart the hotspot. But in JavaScript, you don't really have these tools, and Benchmark.js does not do much to outsmart the JIT. I will show you some examples of optimizations now on the slides, but you should really understand that I'm going to show you them on the source level, but it's not how they happen in reality. So they happen on the more complicated intermediate representations, but for the purposes of the talk, I'm ignoring all the compiler theory, and I'm just doing what I want to do. So what happens with this benchmark with double tilde is that the dog JIT, which is smart enough, it sees that I never changes in the loop. It's a constant, really. The I is assigned some constant string, and you just put it in there. And then it says, oh, but I know how to apply the bitwise negation to the string full of numbers. And it does it. And it does it again. And you end up with just assignment of the constant to a variable, which is not that expensive. It's essentially 0. And this optimization is called constant propagation. And most of the JITs, all of the JITs these days, they do it. So you can say, okay, I can trick the compiler, I can trick the constant propagation. What about if I make the I non-constant? Just generate some string based on the current time, for example. And of course, the JIT will be all panicking and run away. But no, this is a wrong answer, McFly. This is not going to trick the compiler. So the compiler will observe that while it is not a constant, it actually is a loop invariant. So there is no reason to perform this operation again and again in the loop. You can just move it out and perform it outside of the loop. And you're again measuring nothing. You're measuring an assignment of some pre-computed value to a variable. Of course, the computation is now happening in the code, but it's happening kind of outside of like what you're measuring. This is called loop invariant code motion. Again, most JITs do that. They can go further forward, and then they can observe that nobody is actually using J variable. And if nobody is using J variable, then J0 is not used either. And if nobody is using J0, then maybe I is not needed anymore either. And there is no side effects from computing the toString of the date now. So it is all completely dead. So you end up with an empty loop. And of course, then you can even ask if you're a very smart kind of dog JIT, you can ask why then there is a loop, right? And then the loop also goes away. And this is called dead code elimination. And the dead is in the sense that it does not do anything observable, anything useful, anything used by the subsequent code. And the example from before with the split of a string, Firefox is actually smart enough to understand that splitting a constant string by the variable, by some other constant string, and taking the length of the resulting array doesn't actually do anything observable from the outside. So this is all completely removed and eliminated. If you assign this value to somewhere, then it's a different situation. So what you should have figured out from this small intro is that optimizers, they eat micro benchmarks for breakfast and for lunch and dinner, and in the night they also wake up and eat them. And some people really want to create a two-proof micro benchmarks that the optimizers can't eat. My recommendation is usually to not do that at all, like just find something more useful to do. Fix some bugs in your code. But if you really want to at least try, then you should follow some very simple requirements. You should try to avoid this very common optimization, so avoid constants and loop invariants in the dead code. And for the love of God, verify the results of the benchmark that you're doing, because many people just write some benchmark, but they're actually not doing what they expect to do at all, because they don't check the results. And checking the results also combats dead code stuff, because you're now using your computed values. So we can try to fix this benchmark by applying these rules. We create two non-constant values, and we start swapping them in the loop to confuse the compiler, so that the variable we apply, the double tilde to, is no longer a loop invariant. And in the end, we check that everything is kind of good to use the result of the double tilde operation. And this is not bad. Usually should be enough to actually measure something. But if you have a really smart compiler, and our hope is that in the future all the compilers will be very smart, then it's potentially still not enough. Because what compilers can do is that they can take this loop and say, hey, what about if I do twice as less iterations, but I repeat the body inside twice? So some compilers, C++ compilers, do that all the time to small loops. And what happens now is that you swap, and then you swap again. And that's as if you never swapped anything. So the values again become loop invariant for this loop. And because they're loop invariant, you end up with some dead code and some invariant code, and again, not measuring anything. So this optimization is called loop unrolling. V8 does not do it. This slide is actually like from 2012. I have been giving this talk in variants since 2012, and V8 still does not do it. But I want to induce paranoia since 2012 into people, the fear of God. The way you should approach the codes, like you saw that VMs are relatively good in optimizing things. So you should approach a JavaScript code with the presumption of performance. And the presumption of performance is that if you write reasonable code, it should be reasonable fast. And if it's not reasonably fast, then the VM is at fault, not you. But people also have the thing called confirmation bias, which is they think that something is slow, and they write some benchmark, and the benchmarks are, and their code is reasonable, but the performance of this code is bad. And they say, okay, I know this feature of the language is slow, so I will not go and I will not tell anybody that it is slow. I will write a blog post that will warn everybody else from using this language feature. For example, there is this presumption that prototype chains are slow. And people write benchmarks like that. They say, okay, I create a deeply nested prototype chain. How many people know what object create does? I'm just checking that nobody is sleeping there. How many? How many people know what object? How many of you write JavaScript actually? Okay, so not that many. I see. So object.create creates the object with a given prototype. And then if you nest it, you get a deeply nested prototype chain. There is a Lisp tribute on this slide as well. So how many people know Lisp at least? Yeah, okay, yeah, hooray for Lisp. So, and then they write this triply nested loop. For whatever reason it's triply nested, I don't know. And then they access this property on the prototype of a prototype of a prototype of a prototype. And they measure how much it takes outside of this function call. And then they write another function that caches the value of this property outside of this loop, and you just use the variable inside. And then the state-of-art benchmark driver is in the game as well, which calls this function and measures how long it takes. And you measure it, and you discover that indeed, if you look up the property on the prototype many times, it's 8 times slower than just looking it up once and caching the result. And you write a blog post. This is literally taken from a blog post, which says, don't use prototype chains. They are slow, with a big stamp on it. Then, of course, I come and I say, okay, how about I make it harder? What if instead of putting a normal property on the deeply nested prototype, I put the getter on the prototype? And of course, everybody heard that getters are slower than normal properties. And then there is a prototypes in the thing, so it should be many milliards, billions times slower, right? Turns out it is actually faster to make it a getter. And people are really flabbergasted by this, and they say, you are a dark wizard of some sort. But you can look in the generated code. So this is the screenshot of my tool called IRHydra, which shows you what code is kind of generated. This is an intermediate representation used by the compiler. And you can see that if you make it a getter, then suddenly it's inlined into the loop. It says enter inlined, leave inlined, and there is nothing in between those. So because it was just returning a constant, right? And then that constant is just added to this counter thing again and again. So somehow, once we made it a getter, it got inlined. And the same was not happening with the normal property. It was doing this. It was calling this very scary thing called load name generic and looking it up every time again and again in the loop. So it turns out that the blog post was based on the very, very, very old V8, which could not handle the properties defined on the prototypes as well as it could handle the getters defined on the prototypes. So getters it could inline and everything was very good, but the property it would look up through this very slow process again and again. If you try the newer V8, then everything is actually kind of good. And the performance is the same because the newer V8 can handle that well. And when I say newer, it's from 2013 maybe. Somebody was using Node 0.4. something, which used an ancient V8. Okay, everything is good. Everybody is rejoicing. And the thing that you should observe here is that the prototype chain traversal code that goes up the prototype and finds where the property is got loop invariant code moved somewhere out of the loop, and you're not measuring anything again, essentially. So, okay, let's do something completely different. Well, actually the same. So what if I run the same benchmark twice? Like I measured the same function twice for the first benchmark and for the second benchmark as well. Expectation is that nothing changes. Maybe it becomes a little bit faster because there is no cost of optimization anymore. Turns out, no, it's actually become slower for some strange reason. And I was showing you before that compilers are so smart and everything is good and you can dance and be happy and write whatever code you want. But actually, compilers are also very complex, so they have bugs of all sorts inside. And that's what I am trying to show you, that they're full of bugs. And you should be ready to face those bugs. So what happened? So we can again use the IRHydra, and we can see that there are many versions of the same function produced by the optimizing compiler. And the red color means it de-optimized, and then it de-optimized again, and then there is a purple color which also means de-optimized, but a different sort of de-optimization. And then it produced a version that was used after that and did not de-optimize again. So it's the optimizations reached a stable point. But when we look at what kind of stable point it reached, we find that it's a very strange stable point. So the counter variable which accumulates the sum of our opt.prop access, it is now boxed. So you load it from the thing, you add it, and then you box the counter again and again. And the boxing, so V8 uses this representation of numbers, of doubles that is boxed. So you store them in a heap object allocated on the heap, and you store it in there. And you allocate a new one every loop iteration. And of course, that is expensive. You produce a lot of garbage. And that's why it's stabilized on a much slower version. So you can dig through the V8 bug tracker and find the bug. And what was happening is that there was at the very end of the benchmark the line that was printing the counter. And it turns out this line was causing all kinds of shenanigans happen in the V8 internals. And there was a workaround for it. You just need to hide the fact that you're adding this variable to something. For example, you could have force converted it to string with a method call, and then this inference that tries to figure out how to represent variables in the code, like which ones to put on the machine registers as unboxed doubles, for example, it would no longer be confused. And then everything would run just fast. This bug was fixed, so don't put toString anywhere. So most of the bugs that I'm showing you, they're fixed, so you don't have to use any workarounds. Here is for something unfixed, kind of. So again, Stack Overflow question, somebody tries to measure what is, like how much it costs to use getters and setters on the object. And they write this benchmark, and I will accelerate a little bit to make it on time. And on the newer V8, it's three, I don't know, is it million? I can't read numbers. Million, right? Yes, 3 million operations per second. And on an older V8, it is considerably faster. Like it's 800 million, right? And of course, you are, again, very surprised what's happening here. Because kind of V8 people work, and make everything slower, right? Maybe it's time to retire. So if you take this and write it, like remove the benchmark JS from the picture, and you just write this function that does what the benchmark does, define some getter setters and try it in a loop again and again. And you run it once, this function, and you run it twice, and it slows down by a factor of 100 on V8. So yeah, again, our helpful guy that is very surprised. There is a thing called fast representation of objects in V8. And there is a way to check whether your object has a fast representation is to use these internal functions. You need to build V8 and run it with a special flag. But you can check it. And if you run it with a special flag and use that percent has fast properties thing, you discover that when you call this function the second time, the object that is created does not have a fast property representation. And that's why it slows down so much. There is a complicated thing happening here. I don't want to go into the theory details. But how you could work around it is to call object.create on this object. So there is some internal machinery that says if you put an object as a prototype to another object, so here we are not even using the result of object.create, then the V8 force converts it to the fast representation again. So you can call it once, call it twice, does not slow down anymore. Call 3, 4 times, doesn't slow, then slows down. So because there is some polymorphism limit reached in the generated code. Okay. You can say, okay, I will go to the old school methods of creating getters and setters. I will just write it manually, like our ancestors did in 1900. It turns out that's okay, but it's still not as fast as the fastest possible case, right? But at least it does not have these strange drops. It's kind of predictable. So you can then turn to an object-oriented approach. If you were ever a Java programmer, then you can say, okay, object orientation is the answer to everything. If one class is not enough, make 2 classes in the factory. And here I create a box which boxes our value, and then I have getter and setter on this. And then I create this box. Oh, there is yeah, that's how it is. So it's almost equivalent to our previous code. And that's actually the fastest way to do it in V8. V8 is really optimized for this style of object-oriented programming, where you have some classes and you have some methods on the prototypes and stuff like that. So I don't know. You're happy, I'm kind of happy, but I don't know. Depends on your programming style. Maybe you have to adapt. So that's why it's important to know fundamentals. And you can look into other VMs as well. So this talk is about V8 mostly and about V8 bugs, but it doesn't matter that you cannot do the same for the other VMs. So JavaScript core, you can build JavaScript core on the Mac easily. Just check out some source and build it. And it also has this drop-off when you call the first version of function. It's very fast, then a little bit slower. And that's because you can ask it to print you the intermediate representations that the compiler uses in all kinds of stuff and look at it. And like if you know how to read the V8, disassembly and stuff like that, it's easy to read the JavaScript core stuff as well. So there are a lot of code. I don't want you to read it all. I will remove all the stuff that doesn't matter. But you can see that in the first version, it's just checks some preconditions, and then it inlines the set call. And it inlines the get call as well. And it says known callee, so everything is good. But after the third call, in the third call it says, okay, I will no longer do any inlining. I will just start calling through the generic call method. And that's why it slows down, because there is some counters, so like polymorphism limit reached. That's why it's slower. Okay, this third time. We have a little bit of time. I will be fast. So somebody tried to measure whether the function call is faster than the method call or the other way around. So they created a function that does some hashing of some strings, doesn't matter what it does. And then they put this function on the prototype of some object. in the JavaScript, Java style again. So you have an object with a method. An object doesn't contain anything, just this method. And then you compare. You run this function on some strings, and then you run this method, which is just the same function on some strings. And it turns out that the function is considerably slower, and the method is faster, so object-oriented programming wins again. 0-2 to the object-oriented programming. So we can ask this question. And please don't show anybody what I'm going to show you now. It's for you as a GOTO attendees. So if you take this benchmark prototype setup function, which was setting up our benchmark, and you just add these strings inside there, like this, speed your JavaScript with this one weird trick, and then you run it again, then it's the same performance between function and the method. So obviously something is not really right here. Again, our helpful face. So if we look in the IR Hydra, what was happening is that function benchmark was actually never optimized at all. So it was running in the unoptimized version, which is considerably slower than optimized version. And that's why it was slower. And there is an explanation, but I will summarize it for you as yada, 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 yada. So the thing is that function call and the method call were done differently in the V8, and the optimization just was not triggering. It was not counting the right thing to count. And adding the stuff that I added just caused it to be optimized because it started counting the right things. This is kind of fixed, so it should not be a problem anymore again. And but the thing is that we're again measuring the empty loop, because if we look in the IR Hydra, what's happening, the whole hashing code was moved out because the strings that we were hashing were constants. So all the accesses at the constant indices, like length is a constant, or if it's a constant string and stuff like that, everything was moved out. Some of it were computed and folded. Can it be the other way around? So this is the last kind of slides, because I'm running out of time. I work on Dart now, and I work on a Dart VM. But the people who do the compiler from Dart to JavaScript, they come to me and ask questions sometimes, because I used to work on V8. And they were compiling the for in loop into JavaScript, and they were producing this code. And there is this helpful check in there, which is checking that you're not modifying the array, because that's Dart semantics. And you want to throw an exception when you modify array during the iteration. And they said there is a check, and it of course costs something. So if we comment it out, it's 18% faster. Can you help us and make it somehow 18% faster without commenting it out? And I said, well, no problem. You take your code and then you write it like that. So you replace the method call with something strange here. So if you know JavaScript semantics, and the comma operator returns the last evaluated expression, which is this function to call, and then you call it. And this code is never executed, because this is just an exception that never gets to fly out of this code, because you never modified the array. And somehow it makes it faster. Like I measured it, and it really makes it faster. Just to summarize, so somehow we sped up the code by 18% by replacing the method call with some strange stuff that looks like a person whose one eye was like something strange happened to it, and in the code that never executes, and we sped up everything. So what is happening there is that V8 does not know so this code was never executed, and V8 really relies on the information collected by the executed code to optimize it. And because it was never executed, it does not know what's happening there. And the non-executed method calls and non-executed property accesses were treated differently in the V8. So I replaced the non-executed method call and with a non-executed property access, and it just helped to optimize it. It helped it to understand that that was never executed, and helped it to understand that the length never changes, because like V8 can see that there is only array access and no functions calls in the code, so it can just assume that this is all that code and make it that, and yeah, so this is explanation, doesn't matter. So I really recommend to take a look on your algorithms first, and then start micro benchmarking. And wait a second. There was a first example with this and a strange use hasm directive. Again, we can look at it in the our Hydra and discovered that the V8 was continuously de-optimizing the function where we inlined all the stuff inside. And there was the opt marker in a strange place saying strange things. And if you see the code like that, if you see the situation like that where your function is continuously being de-optimized and optimizations never stabilize, then you should just go and file a V8 bug really, because it's a V8 bug, not your bug. There is again explanation, doesn't matter. There is a more sane workaround than putting this huge comment. So the reason why the huge comment worked is that because V8 relies on the size of the source code to make inlining decisions due to some historical artifacts, which would be eventually fixed, I suspect. There is a much sane workaround instead of disabling inlining is to just add some truncation to this load from the array. So please never assume that the language feature has to be slow. Do go and demand from your like closest senators or whatever and people in the parliament to make JavaScript features fast. Write bugs in the V8 bug tracker, and VM people are really your friends. I'm your friend, even though I'm not a V8 person anymore. So remember to rate this session, whatever. Thank you very much for your attention.